Hello guys, welcome to Physics Grad. In this video, we are going to study about Euler-Lagrange equations. So this is a very important mathematical result which we will be using in our classical mechanics video lectures. So let us begin. Let us consider a function j of y which is defined as follows. It is a definite integral from x1 to x2 of some function L, which is a function of x, y of x, y dash of x, and this integration is over the variable x. Now here x1 and x2 are constants. Y of x is a twice differentiable and continuous function of x, and y dash is defined as dy by dx, and the function L, which is a function of x, y and y dash, is also twice differentiable and continuous with respect to x, y and y dash. So this is where we are going to start. Now let's say that the function j of y has a local minima at y equal to f, some value f. Also, I am going to define another function called eta of x, which has at least one derivative, or you can differentiate it at least once, and eta of x1 equal to eta of x2 equal to 0. So note this is something which we need to keep in mind. So I'm going to define, some function eta of x which can be differentiated at least once, so which means it is at least once differentiable function, and it vanishes at the points x1 and x2. Okay. Now, because of our assumption that j of y has a local minimum at y is equal to f, this implies that j of f is always less than or equal to j of f plus epsilon times eta, where epsilon is close to 0. So this ensures that it is in the locality of f, and we have assumed that the function j of y has a local minima at the value of f. So in the locality, the value of the function at f is always going to be less than or equal to the value of the function just beside f. That is what this inequality is saying. Because epsilon is very close to 0, that means this change in f is going to be very small, which means that this value is going to lie in the locality of f. Okay, I hope that is clear. So with this setup, since this is going to vary the value of f by a very small amount, we are going to call epsilon eta. I'm going to define this as the variation of f. And I'm going to denote it as del f. Okay, so I hope this much is clear. So this is the formalism. Let me once again repeat it. So we are going to consider a function j of y which is defined in the following way, or which has a form of which is of this kind, which is a definite integral of some function L which depends on x, y of x and y dash of x, where x1 and x2 are constants, y of x is twice differentiable and continuous function of x, y dash of x is basically defined as dy by dx, and the function L is also twice differentiable and continuous with respect to x, y and y dash. And we are going to consider a function j which has a local minimum at the value y equal to f, and therefore it must satisfy this inequality, which basically says that the value of the function is minimum in the locality around f. And we are going to define this value epsilon eta as the variation of f, which is denoted by delta f. Okay. So now consider this function phi of epsilon, which is defined as j of f plus epsilon eta, which is basically this function. Now, when will this function, which is phi of epsilon, have a minimum? So when or for what epsilon value phi of epsilon will be minimum. So we know that this particular value goes to a minimum when the argument is just j of f. So this implies for this condition, or for phi of epsilon to be minimum, which means this function must be minimum, which is true only when f plus epsilon eta is equal to f. So that can happen only when epsilon is equal to 0. So therefore phi epsilon minimum is equal to phi of epsilon equal to 0, which is equal to phi of epsilon, which is basically j of f. Okay. So this implies, we know that for some function f, or I'm not going to use the same notation, some function g of x has a minimum when g dash of x equal to 0. So this condition, what does this imply? This says that, so since phi of x has a minimum, phi of epsilon has a minimum when epsilon equal to 0, this implies that phi dash of epsilon equal to 0 when epsilon equal to 0, right? So this is basically this result. Any function g of x has a minimum or a maximum when g dash of x equal to 0, and in this case when epsilon equal to 0, phi of epsilon is going to have a minimum, which means phi dash of epsilon should be equal to 0 when epsilon equal to 0. Okay, we are good to go. So this phi dash of epsilon is basically d phi by d epsilon, and this is equal to 0 at epsilon equal to 0. So this should be equal to 0. So this is nothing but this is nothing but d by d epsilon of, what is phi of epsilon? Phi of epsilon is nothing but j of f plus epsilon eta. So this at epsilon equal to 0. So this is nothing but d by d epsilon integral x1 to x2 L dx, right? So I have to evaluate this at epsilon equal to 0. So what is this value? Oops. So this becomes equal to integral x1 to x2 dl by d epsilon dx at epsilon equal to 0. Okay. So now all we need to find is what is dl by dx. Okay, so let's do that. So dl by dx, sorry, d epsilon, we need to find dl by d epsilon. So we need to find this. So how is that? How do we find that? So we find that in the following way. So this is basically dou L by dou x into dx by d epsilon plus dou L by dou y into dy by d epsilon plus dou L by dou y dash into dy dash by d epsilon. Okay, now dx by d epsilon is going to be 0 because epsilon is independent of x. So this term goes to 0. Now what about these two terms? We had defined L of, so in this particular case what we are going to do is that we have basically substituted, if we go back here, yeah, so here for y we have substituted it as f, and when we are considering j of f plus epsilon eta, we are basically substituting y as f plus epsilon eta. So this implies y equal to f plus epsilon eta. So using this result, we are going to go back here now. So here we have y equal to f plus epsilon eta and y dash equal to f dash plus epsilon eta dash. So this implies dy by d epsilon will be equal to eta and dy dash by d epsilon will be equal to eta dash. So we are going to use this result in these equations, which will give us dl by d epsilon is equal to, so let's go back here, this is equal to dou L by dou y into dy by d epsilon, which is nothing but eta, so into eta, plus dou L by dou y dash into dy dash by d epsilon, which is nothing but eta dash into eta dash. So what is this going to be? So this is the final result. Now we want to evaluate this at epsilon equal to 0. And we note that for this case, y equal to f plus epsilon eta at epsilon equal to 0 is nothing but f. So this implies y is equal to f and y dash is equal to f dash. And I am going to use this in this equation, and which will give me dl by d epsilon is equal to dou L by dou f into eta plus dou L by dou f dash into eta dash. Alright, so far so good. So now we are going to go back here and substitute our result in this equation. So this is going to become integral x1 to x2 dou L by dou f into eta plus dou L by dou f dash into eta dash. So I have basically made this substitution here and I am getting this result, which is basically what I have done here. So this is at epsilon equal to 0, and that is what we get here. So this times dx. Okay, so this becomes equal to integral x1 to x2 dou L by dou f times eta dx plus integral x1 to x2 dou L by dou f dash into eta dash dx. Now let us simply consider this part, and we are going to apply integration by parts to expand this. So we are going to use integration by parts. So using that, this particular integral will become dou L by dou f dash times eta. I am basically integrating eta dash, which becomes eta, and apply the limits x1 to x2 minus integral x1 to x2 times, I am again integrating eta, and now I have to differentiate this function, which becomes d by dx times dou L by dou f dash into dx. So this is just using integration by parts. I have expanded this expression. But note that we had defined eta in such a way that, where is it? Yeah. So we had defined eta such a way that it satisfies this condition. So this implies, okay, where are we? Yeah. So this implies that since eta of x2, so since eta of x2 equal to eta of x1 equal to 0, this term goes to 0. And all we are left with is this term. So I can replace this with this. So let's do that. So this becomes equal to integral x1 to x2 dou L by dou F times eta dx minus integral x1 to x2 times eta into d by dx times dou L by dou F dash times dx, which is basically substituting this result. So what does this give us? So this becomes integral x1 to x2 times eta into dou L by dou F minus d by dx times dou L by dou F dash into dx, and this must be equal to 0. So this must be equal to 0. Now eta is a non-zero function from x1 to x2, and dx is a very small number but not equal to 0. So the only way this expression can go to 0 is if this expression becomes equal to 0. So therefore we have the result dou L by dou F minus d by dx times dou L by dou F dash is equal to 0. So this result is basically a second order partial differential equation. And this equation is called as the Euler-Lagrange equation. So this function L is called the Lagrangian. So L is called the Lagrangian, and that's where the name comes from. So where is this used? What is the whole point of deriving this equation? So what we have done from this exercise is that we have basically found out the condition for jy to be minimum. So what have we found out? The condition for j of y to attain minimum, or in general an extrema, is that this equation must be satisfied. This particular equation must be satisfied. So that is basically the Euler-Lagrange equation, and the result is that dou L by dou F minus d by dx times dou L by dou f dash. This should be equal to 0. So if this condition is satisfied, j of y is going to have a minimum. Okay. So when can this condition be satisfied? This condition is satisfied only when y becomes equal to f. So this implies dou L by dou y minus d by dx dou L by dou y dash becomes equal to 0 at y equal to f, which is where we assumed j of y has a minimum, and that is what the Euler-Lagrange equation helps us to find. It helps us to find the minimum of a function which is defined in this manner. So yeah, that's it. Thank you for watching. I will see you in the next video.